I started watching The Mentalist last night, and it's so peak. So peak! I only watched like the first 2 episodes, but like it's actually so good. Like the acting is really good. Like acting is like scarily good. You know, because like it's, I mean, like it is like a detective thriller, you know, and like some of the crimes that it deals with are quite serious. Like the acting is actually so good that you feel like the tension. You know, it's crazy. It's I mean, it's gonna be the first 2 episodes. Maybe it goes absolutely downhill, but I don't think it does based on the edits I've seen on Instagram. But yeah, I mean, like really strong pilot, and then the next 2 episodes there, which is so good, so good. Great acting, great cinematography, great writing. Like it's really good so far, and I'm aware it gets very high ratings too. I mean, 8.2 on IMDb for a 7-season show is like pretty damn good. And 5 out of 5 stars on this. Like, what is Breaking Bad even? Cause like that's like top tier. Yeah, 9.5, right? So like yeah, like it's not Breaking Bad. But like 8.2 is still really good. Not that I care about ratings anyway. I mean, I feel like the audience for Breaking Bad would be quite different to the audience for this. So, but yeah, Patrick Jane is a really cool main character, and really interesting too. You know, but then like also like just like the other characters too. You know, like yeah, it kind of subverts my expectations. You know, like I thought it'd be like the cliche kind of thing, but like I like how like Cho and the other guy that I can't remember this tall guy's name, but like they actually have his back, Patrick's back. You know, it's not like I don't know, the stereotypical show where like they all hate the main character because he's so like arrogant. You know, like no, like they actually like do respect him, which is cool. And yeah, I'm looking forward to keep watching it. Anyway, category theory for programmers, chapter 6. I thought I finished chapter 4, but no, I'm actually now on chapter 6. No, I'm on chapter 5. Never mind. I thought I finished chapter 5. I'm on chapter 4. That's right. I finished chapter 4. So now I'm on chapter 5, which is products and co-products. So let's go ahead and open that up in Ocular, I mean. Yeah. And yeah. So again, I already know quite a bit about products and I mean, I say quite a bit. I know what products and co-products are. Product is a this and this type. Co-products are this or this type, this or that. And then it's this and that. So like tuples would be a product type, and enums would be a co-product, and then an abstract data algebraic data type would be like a mix of both. The ancient Greek playwright Euripides once said, "Every man is like the company he is wont to keep." We are defined by our relationships, basically. Nowhere, like such a random quote that is not even used like in that context, but nowhere is this more true than in category theory. If you want to single out a particular object in a category, we can only do this by describing its pattern of relationships with other objects and itself. Right, so these relationships are defined by morphisms. Yeah. So like I don't know if category theory has the notion of types. Like you have objects which can contain stuff, but like those are like objects, you know? Like what's a type? I guess there's a common construction in category theory called the universal construction for defining objects in terms of their relationships. One way of doing this is to pick a pattern, a particular shape constructed from objects and morphisms, and look for all its occurrences in the category. Right, a shape. So a shape is defined by objects and morphisms, which we can kind of think of like as like variables and functions within a something, maybe? I don't know. If it's a common enough pattern and the category is large, chances are you'll have lots and lots of hits. The trick is to establish some kind of ranking among those hits and pick what could be considered the best fit. So this process is reminiscent of the way we do web searches. A query is like a pattern. A very general query will give you a large recall. Lots of hits. Some may be relevant, others not. To eliminate irrelevant hits, you refine your query. That increases its precision. Finally, the search engine will rank the hits, and hopefully the one result that you're interested in will be at the top of the list. I guess. Initial object. The simplest shape is a single object. Okay, obviously there are many instances of this shape as there are objects in a given category. That's a lot to choose from. I guess so, if it's a plentiful category. We need to establish some kind of ranking and try to find the object that tops this hierarchy. So there's like a, what's the word? A dominant object? That only means at our disposal of morphisms. If you think of morphisms as arrows, then it's possible but I thought they were arrows, then it's possible, like that is like another word for them, and that there is an overall net flow of arrows from one end of the category to another. This is true in ordered categories. For instance, in partial orders, we can generalize a notion of object precedence by saying that A is more initial than object B if there's an arrow, a morphism, going from A to B. Oh, okay. Right, so like the parent. I mean, not the parent per se, but yeah. But what if it's an isomorphism? We would then define the initial object as one that has arrows going to all other objects. Right. Obviously, there is... Hold on. So these are... So, like, if the arguments for a... What even is an object, though? Like, I don't really fully understand that. We would then define the initial object as one that has arrows going to all other objects. Obviously, there is no guarantee that such an object exists, and that's okay. A bigger problem is that there may be too many such objects. The recall is good, but precision is lacking. The solution is to take a hint from ordered categories. Okay, they allow at most one arrow between any two objects. Right, there's only one way of being less than or equal to another object, which leads us to this definition of the initial object. The initial object is an object that has one and only one morphism going to any object in the category. Sure. However, even that doesn't guarantee the uniqueness of the initial object if one exists, but it guarantees the next best thing, uniqueness up to isomorphism. Isomorphisms are very important in category theory, so I'll talk about them shortly. For now, let's just agree that uniqueness up to isomorphism justifies the use of the in the definition of the initial object. Have you even mentioned have you even talked about what isomorphisms are yet? I mean, it's pretty obvious. It's just like it's an isomorphism. I don't know. Here are some examples. The initial object is in a partially ordered set, often called a poset, or poset, is its least element. So partially. Oh yeah, wait. Sets can be ordered. Okay. I mean, I guess so, but like, I thought that they were just inherently unordered. So does it mean a list is just an ordered set? But can sets have? But like sets can't have duplicates, right? I guess that's the main thing. Also, lists have like a kind of like lists have like an arbitrary order. You know, like lists don't have like a rule for the order. Like it's just like if I put it this way, it's this way. You know. Some don't have an initial object, like the set of integers. Positive and negative, yeah, where there's an equal relations for morphisms. Sure. So they just don't have it. In the category of sets and functions, the initial object is the empty set. Okay, remember an empty set corresponds to the Haskell type void, and the unique polymorphic function from void to any other type is called absurd. Why? I thought empty set was oh no, it's not unit. No, it's void, yeah, like true void. A function from void to A is absurd, but it's not. But it doesn't exist, right? I mean, like, I guess it could exist, but like, you can just define it as absurd. So that's the initial object. So A is more terminal than the object B if there's a morphism going from B to A. The reversal of direction. From B to A. Yeah, that makes sense. We'll be looking for an object that's more terminal than any other object in the category, again with such uniqueness. Okay. So like, I don't know, like would a string, would like the null terminator be a terminal object? Probably not. Yeah, probably not actually. Or like But would it though? I mean, I don't know. The terminal object is an object, like right now this is really abstract. The terminal object is the object with only one morphism coming to it. Yeah, okay. And again, terminal object is unique. I mean, it makes sense, right? Isomorphism, which I'll show shortly. But first, let's look at some examples. In a poset, the terminal object, if it exists, is the biggest object. In the category of sets, the terminal object is a singleton. We've already talked about singletons. They correspond to the void type in C++ and units in Haskell. It's a type that only has one value implicit in C++ and explicit in Haskell. Why is it a terminal? In that case, denoted by that. We've also established that there is one and only one pure function, which is unit. So all the conditions for the terminal object are satisfied. Okay, so like there's one function from to it. Okay, fair enough. Notice that in this example, the uniqueness condition is crucial because there are other sets. Actually, all of them except for the empty set that have incoming morphism from every set. For instance, there is a Boolean valued function, a predicate defined for every type, but bool is not a terminal object. There's at least one more bool valued function. Yeah. Yes. Insisting on uniqueness gives us just the right precision to narrow down the definition of the terminal object to just one type. Duality. You can't help but to notice a symmetry between the way we define the initial object and the terminal object. Yeah, the only difference between the two was the directional morphisms. It turns out that for any category C, we can define the opposite category, COP, okay. Why is it OP? Opposite, I guess, OP for opposite, just by reversing all the arrows. What? The opposite category automatically satisfies, well that's interesting, all the requirements of a category, as long as we simultaneously redefine composition. If original morphisms, F A to B and G B to C compose to H A to C, then the reverse morphisms B to A and C to B will compose to C to A. Yeah. And reversing the identity arrows is a no-op. No opposite. That is actually kind of hilarious how that works out as a pun. Okay. Sure. Is it OP like this though? Like with like O and P as like separate variables? Because that was kind of weird, but I'm gonna assume that's correct and just write it like so. So okay, this is with noting. So 5.3 duality. For every category C, there exists. Sorry, that should be math typeface bold. Right. Yep. There exists the opposite category. What? C OP. That seems correct. I still need to set up my keybind, by the way. Like I mentioned in like the previous video. I won't explain it again, but like yeah. Just so like a more easy way to switch between windows without me having to like memorize what like the different keybinds for each different window. Like a workspace, sorry, like just have like a workspace view that I can then press a number between to switch between. So yeah, so like how's that work though? Like, can I have, like, a morphism from unit to bool, but also unit to everything else? Right? Like, does there exist an opposite category where the rule of, I don't know, like having one output for each input, or at least one at most one output for each input, like, is that a rule that needs to be satisfied or not? Because that's interesting. I guess not. I don't see why that'd have to be a rule. But like, surely for programming. Well, no, actually it wouldn't be, right? Like, I could have unit be... Well, no, because like, if false can go to unit... Well, no, it's bool to unit, right? Like, if if I have a function that takes any bool, right, and makes a unit, how do I take the opposite of that? Like, do I have it go to false or to true? You know, what level of context would be required there? Duality is very important and a very important property of categories because it doubles the productivity of every mathematician working in category theory. For every construction you come up with, there is its opposite, and for every theorem you prove, you get one for free. The constructions in the opposite category are often prefixed with CO, as you have products and coproducts, right? Monads and comonads, really? Cones and cocones, limits and colimits. I've heard of colimits. I've not heard of comonads? How's that work? Extraction. I mean, if you look at a Husserl monad, yeah, but a monad is like a rule, right? Like, take like the bind, right? The bind operator, which is MA to A to MB to MB. Like, if you were to take the opposite of this, it'd be MB. So like these are unaffected, but then but instead here it'd be a function from MB to A, right? I mean, not unaffected, but like the A to B, like doesn't really matter. Like, those are just variables. Well, what matters really is that this gets reversed. So I would take a monad and return this like a single value somehow. I don't know. How does that work? Cobind, is that a thing? Yeah, like generally in maths, code does mean opposite. So there are no comonads though, because reversing the arrow twice gets us back to the original state. Sure. It follows then that a terminal object is the initial object in the opposite category. So it's the co-initial object then. Isomorphisms. As programmers, we are well aware that defining equality is a non-trivial task. What does it mean for two objects to be equal? Do they have to be occupy the same location in memory? Pointer equality. Pointer equality? Is that what they call it? I call it reference equality. Or is it enough that the values of all of their components are equal? Well, yeah. So there's structural equality and referential equality. Are two complex numbers equal if one is expressed as a real and imaginary part and the other as modulus and angle? Good question. In value, yes, but in form, no. Jesus. Yeah, actually, I guess that's a thing as well. Like, there's structural equality, but there's also, like, value equality. Like, can they evaluate to the same thing? Like, I guess there's a word for it. Is it called, like, loose equality or something like that? Where, like, you can loosely be equal to something. Like, let's say I have true, right, which is able to cast to a 1 as an integer for some reason. Then that would mean that true would equal 1 loosely, right? But like, it wouldn't equal it structurally, and it wouldn't equal it, well, referentially is whatever, right? But mathematicians haven't figured out the meaning of equality. They have the same problem with multiple competing definitions for equality. There's the propositional equality, intentional. That's not the same thing, right? Yeah, no. That's different. Intentional and intentional with an S. English, bro. Extensional equality and equality as a path in homotopy type theory. And then there are the weaker notions of isomorphism and even weaker of equivalence. Yeah, like weak equality, right? The intuition is that isomorphic objects look the same, they have the same shape. Okay, so shape matters. It means that every part of one object corresponds to some part of another object in a one-to-one mapping. As far as our instruments can tell, the two objects are a perfect copy of each other mathematically. Yeah. So if there exists a perfect isomorphism, yeah. So like isomorphic means that for every input there is exactly one output, and every single input has an output. I believe it's equivalent to a bijection, right? Like with functions, the idea of a bijection, which is both subjective and injective, and then an isomorphism is a general term there for category theory, I guess. Mathematically, it means, so wait, so would a co-isomorphism be one where there exists no morphism at all? I don't know, bro. Mathematically, it means that there is a mapping from object A to object B, and there's a mapping from B back to object A. Oh, that too. Yeah, both ways. And they are the inverse of each other. In category theory, we replace mappings with morphisms. An isomorphism is an invertible morphism, or a pair of morphisms, one being the inverse of the other. We understand the inverse in terms of composition and identity. Oh, yeah. Sorry, no. A bijection is to do with like sets. A morphism an isomorphism is a property of the actual arrow, like the actual function. But like I believe you could also have an isomorphic object, or like isomorphic category, or like something like that. Wait, what am I saying? Because like no, never mind. Because like a morphism is from type to type, not value to value. Well, not necessarily anyway. We understand the inverse in terms of composition and identity. Morphism G is the inverse of morphism F if their composition is the identity morphism. Yeah. Okay. Wait, inverse? Wait, no, that's not what I expected. Well, no, I mean, it is what I expected, right? Like, if I've, like, obviously, like, the idea that I think of here is, like, I don't know, multiply and divide, or, like, yeah, like times x and then, like, divide by x. But if I have, let's say I have a morphism from integers to strings, right? And then back, vice versa. So, like, 1 to the string 1, and then the string 1 to the integer 1, right? This actually, okay. Let's say I have a morphism from integers to bools, right? So I have 1 to true and true to 1. That's an isomorphism, because if I were to compose the function int to bool and bool to int, I'll get int to int, so I'll get 1 back. When I said that the initial terminal object was unique up to isomorphism, I meant that any two initial objects are isomorphic. Why is terminal in brackets? That's actually easy to see. Let's suppose that we have two initial objects, I1 and I2. Since I1 is initial, there is a unique morphism F from I1 to I2. It's unique, yeah. By the same token, since I2 is initial, there is a unique morphism from I2 to I1. What's the composition of these two morphisms? The identity. The composition G of F must be a morphism from I1 to I1, but I1 is initial, so there can only be one morphism given from I1 to I1. Since we are in a category, we know that there is an identity morphism from I1 to I1, and since there is room for only one, that must be it. Therefore, G of F is equal to identity. Similarly, F of G must be equal to identity, blah 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 blah. Okay, notice that in this proof, we use the uniqueness of the morphism from the initial object to itself. Without that, we couldn't prove the up to isomorphism part. But why do we need the uniqueness of F and G? Because not only is the initial object unique up to isomorphism, it is unique up to unique isomorphism. In principle, there could be more than one isomorphism between two objects, but that's not the case here. This uniqueness up to unique isomorphism is the important property of all universal constructions. That's a mouthful, man. Mahjong society, bro. Products. The next universal construction is that of a product. We know that. I didn't quite grasp what a universal construction is. We know that a Cartesian product of two sets is. Sorry, what it is a set of pairs. A set of pairs, yeah. But what's the pattern that connects the product set with its constituent sets? If we can figure that out, we'll be able to generalize it to two other categories. All we can say is that there are two functions, the projections from the products to each of the constituents. In Haskell, these two functions are called first and second, and they pick respectively the first and second component of a pair. Yeah. Here the functions are defined by pattern matching their arguments. The pattern that matches any pair is xy, and extracts these components into variables x and y. What is pattern matching, by the way? Like, in terms of category theory, what is pattern matching? Like, I believe pattern matching is like the inverse of constructing, right? Like the act of constructing a tuple, for instance. Pattern matching is just kind of like destructing it. But like when we think of destructing, we think of like, you know, like memory, taking it off the heap, whatever. But like I mean destructing is in like co-construction. What? Co-construct? That's weird. Okay. right? Because like here I take, well no, this isn't it. But like with pattern match, sorry, with construction, right? I take an A and a B, and then I construct an A and B. With pattern matching, I take an A and B and destruct it into individual variables A and B, A and then B, but like separately. That's basically what pattern matching is, right? It's destruction. So you have construction and like, I mean, I feel like destruction isn't the right word, you know. What is the true opposite of construction? Sorry, if pattern matching represents the opposite of construction, what would be the term? Destruction? Co-construction? Like, you could think of pattern matching being like the combination, I mean, for a tuple, being the combination of first and second, right? So first gives you the first one, second takes a tuple and gives you the second one, and then the combination of those two would give you both, right? Not composition, but the combination, I guess. And that's why if I search for products on Wikipedia, holy moly, that was so vague. If I search for product type on Wikipedia, the diagram I get, hilarious. Can I get category theory, please? Are you dead ass right now? Category theory. Yeah, or just the product. Sorry. So then you get this thing, this function, and the idea is that for some variables x and y, I have these pi1, pi2, right? So like this is my tuple. This is first, like pi1 is first, pi2 is second. Yeah. Damn it, dude. There's y to x1, x2 as well. Yeah, never mind. I do figure out what y is. For every object y, there exists a unique morphism y to x1, x2. But like, what is y then? I swear, like, I'm close, but whatever. Here are the functions are defined by pattern matching. Yeah. Sorry, what did Claude say? Okay. These definitions can be simplified even further with the use of wildcards. Yeah. And in C++, we do have this. Equipped with this seemingly very limited knowledge, let's try to define a pattern of objects and morphisms in the category of sets that will lead us to the construction of a product of two sets A and B. This pattern consists of an object C and two morphisms P and Q, connecting it to A and B respectively. So there's two sets A and B. There's an object C, and then two morphisms P and Q. So P C to A, Q C to B. Okay. All C's that fit this pattern will be considered candidates for the product. There may be lots of them. For instance, let's pick as our constituents two Haskell types int and bool, and get a sampling of candidates for their product. Here's one. Int can. Okay, here's one int. Can int be considered a candidate for the product of int and bool? Yes, it can, and here are its projections. Right. Just true by default, I guess. Okay. That's pretty lame, but it matches our criteria. Here's another one. Int bool is a tuple of the elements or a triple. Where a tuple is 2 and a triple is 3. That's not confusing at all. Here are two morphisms that make it a legitimate candidate. We are using pattern matching on triples. P and Q. Okay, but we ignore the second one, right? It only carried the intermediate part. The second was too big. It spuriously duplicated the int dimension. Yeah, but we haven't explored yet the other part of the universal. See that this is the diagram. We haven't explored yet the other part of the universal construction, the ranking. We want to be able to compare two instances of our pattern. We want to compare one candidate object C and its two projections P and Q with another candidate object C prime and its two projections P prime and Q prime. We would like to say that C is better than C prime if there's a morphism M from C prime to C, but that's too weak. better. We also want its projections to be better or more universal than the projections of C prime. What it means is that the projections P prime and Q prime can be reconstructed from P and Q using M. So wait, what's M? C is better than C prime if there is a morphism M from C prime to C. From C prime to C, okay. So P prime is P and M, or MP, I guess, and then MQ. Right, but like, what is C prime and C? Like, I don't really understand that. Like, A and B are the other two types. C is the product type? But what's C prime? Another way of looking at these equations is that M factorizes P prime and Q prime. Factorizes is the term. Factorizes. Is that like the opposite of composition? Just pretend that these equations are in natural numbers and the dot is multiplication. Well, M is a common factor shared by P prime and Q prime. Sure. Just to build some intuitions, let me show you that the pair int bool with the two canonical projections, first and second, is indeed better than the two candidates I presented before. So I have int and to int bool bool, right? So int to int is just int P, int to bool is Q, and then to get to int, from int to int bool, like, I don't understand how M, like why is it in terms of M? Why isn't this like the composition of P and Q, you know? Or like the combination of P and Q? I guess you can't really represent that, maybe? What? You're close tweaking, bro. I want to know. Save you, Gemini. Destructure. Wait, construct? Wait, so there's to construct and to destructure. But destruct would be to destroy it. But destructure would be to undo it. That's weird. That's actually really weird, yeah. So you have so you have to construct and to destruct, right? So to create something and then to destroy it. But then you have to structure, which is to like put something into a structure. Okay, makes sense. And then to destructure, which is to get out of that structure. Okay, you know, that makes sense, right? I structure something and then I destructure it, and then or deconstruct it. So then that's I guess the other one, but I do like destructuring for that then. Co-construction is building with others, yeah. Just a funny thing there. The mapping M for the first candidate is int to int bool, but like this isn't useful, right? Like this isn't usually how you make product types, because like you pass two inputs, which is what I thought P and Q would be. Like why is there no morphism that combines P and Q here? Indeed, the two projections P and Q, yeah, the M for the second example is similarly uniquely determined. We were able to show that int bool is better than either of the two candidates. Sure. Let's see why this opposite is not true. Can we find some M prime that would help us reconstruct first and second from P and Q? In our first example, Q always returns true, and we know that there are pairs whose second complement is false. We can't reconstruct second from Q. Right. The second example is different. We retain enough information after running either P or Q, but there is more than one way to factorize first and second. Okay. Yeah, that's true. Putting it all together, given any type C with two projections P and Q, there's a unique M from C to the Cartesian product. Okay. So by the way, the product does come from Cartesian product, which is interesting. But like the names product and sum come from the what's the word? The cardinality of the sets. So like if I have A and B, the total number of combinations of A and B would be the size of A, like the type A, times the size of type B, or like the number of elements in each multiplied. That's the number of like combinations. But with some types, because it's this or that, then the number of possible total combinations or possible states, I guess, is just the number of types. So it's the cardinality of the first one plus the second one. So like if I have int or bool, it'd be the total number of ints plus the total number of bools. Whereas for products, if it was int or int and bool, then it would be times. But I'm guessing product by itself just comes from Cartesian product, and then the coproduct is just opposite of that. But anyway, so there's a unique M from C to the Cartesian product A, B that factorizes them. It combines P and Q into a pair. Yeah, it does. So why does the diagram not kind of like represent that? That makes the Cartesian product AB our best match, which means that this universal construction works in the category of sets. It picks the product of any two sets. Now let's forget about sets and define a product of two objects in any category using the same universal construction. Such a product doesn't always exist, but when it does, it is unique up to a unique isomorphism. Right, a product of two objects A and B is the object C equipped with two projections, such that for any other object C prime equipped with two projections, there is a unique morphism M from C prime to C that factorizes those projections. Ooh. A higher order function that produces the factorizing function M from two candidates is something called the factorizer. In our case, it would be the function this. So it takes PQ and produces a function. But how? Oh wait, no, that makes sense. Okay, coproduct. Like every construction in category theory, the product has a dual, which is called the coproduct. When we reverse the arrows in the product pattern, we end up with an object C equipped with two injections, I and J, morphisms from A and B to C. Wait. Yeah? Yeah, okay. Like, pattern matching is the opposite, but like, yeah, I guess this is like the true co-product. So now I have I and J, which both point to C. So, the ranking is also inverted. Object C is better than object C prime. That is equipped with the injections I prime and J prime. If there's a morphism M prime from C to C prime, that factorizes the injections. The best such object, one with a unique morphism connecting it to any other pattern, is called a coproduct, and if it exists, is unique up to unique isomorphism. Okay, so I and J, C to M. Sorry, C follows M to C prime. But it points inwards. A coproduct of two objects A and B. Okay. In the category of sets, the coproduct is a disjoint union of two sets. An element of the disjoint union of A and B is either an element of A or an element of B. If the two sets overlap, the disjoint union contains two copies of the common part. You can think of an element of a disjoint union as being tagged with an identifier that specifies its origin. For a programmer, it's easier to understand a coproduct in terms of types. It's a tagged union of two types. C++ supports unions, but they are not tagged. It means that in your program, you have to somehow keep track which member of the union is valid. To create a tagged union, you have to define a tag, an enumeration, and combine it with a union. For instance, a tagged union of an int and a char pointer could be implemented as this. Yeah. The two injections can either be implemented as constructors or as functions. For instance, here's the first injection as a function phonum. And it injects an integer into contact. A tagged union is also called a variant. And there's a very general implementation of a variant in the Boost library, Boost variant. In Haskell, you can combine any data types into a tagged union by separating data constructors with a vertical bar. Yep, love that. Here, phonum and email address serve both as constructors, injections, and as tags for the pattern matching. More about this later. For instance, this is how you would construct a contact using a phone number. Unlike the canonical implementation of the product that is built into Haskell as primitive pair, the canonical implementation of the coproduct is a data type called either. Okay, it is parameterized by two types, A and B. Yeah. So we can define a factorizer for the coproduct. Given a candidate type C and two candidate injections I and J, the factorizer for either produces the factoring function. So two functions on the left A gives you I on A. Okay. Asymmetry. We've seen two sets of dual definitions. The definition of a terminal object can be obtained from the definition of the initial object by reversing the directions of arrows. In a similar way, the definition of the coproduct can be obtained from that of the product. Yet, in the category of sets, the initial object is very different from the final object, and coproduct is very different from product. We'll see later that product behaves like multiplication, with the terminal object playing the role of 1, whereas whereas coproduct behaves more like the sum, with the initial object playing the role of 0. Why? In particular, for finite sets, the size of the product is a product of the size there's that. The size of the product is a product of the sizes of individual sets, and the size of the coproduct is the sum of the sizes. This shows that the category of sets is not symmetric with respect to the inversion of arrows. Notice that while the empty set has a unique morphism to any set, it is no morphism coming back. The singleton set has a unique morphism coming to it from any set, but it also has outgoing morphisms to every set. As we've seen before, these outgoing morphisms from the terminal object play a very important role of picking elements of other sets. The empty set has no elements, so there's nothing to pick. It's the relationship of the singleton set to the product that sets it apart from the coproduct. Consider using the singleton set, with units, and as yet another vastly inferior candidate for the product pattern. Equip it with two projections P and Q, functions from the singleton to each of the constituent sets. Each selects a concrete element from either set. Because a product is universal, there's also a unique morphism M from our candidates, the singleton to the product. This morphism selects an element from the product set, it selects a concrete pair. It also factorizes the two projections. But so, what are the constituent sets? When acting on the singleton value unit, the only element of a singleton set, these two equations become. Since M unit is the element of the product picked by M, these equations tell us that the element picked by P from the first set P unit is the first component of the pair picked by M. This is in total agreement with our understanding that elements of the product are pairs of elements from the constituent sets. There's no such simple interpretation of the coproduct. We could try the singleton set as a candidate for a coproduct in an attempt to extract the elements from it, but they would have two injections going into it rather than two injections going out of it. Neither would the unique morphism from the coproduct to our singleton. The category of sets just looks very different when seen from the direction of the initial object than it does when seen from the terminal end. This is not an intrinsic property of set, it's a property of functions, which we use as morphisms in set. Functions are in general asymmetric. Let me explain. A function must be defined for every element of its domain set. In programming, we call it a total function, but it doesn't have to cover the whole codomain. True. But it can, right? And I guess that's what a symmetric function is, or like a symmetric relation. We've seen some extreme cases of it. Functions from a singleton set. Yeah. Actually, functions from an empty set are the real extremes. When the size of the domain is much smaller than the size of the codomain, we often think of such functions as embedding the domain in the codomain. For instance, we can think of a function from a singleton set as embedding its single element into the codomain. I call them embedding functions, but mathematicians prefer to give a name to the opposite. Functions that tightly fill their codomains are called surjective or onto. Okay, surjective. Yeah. So like if I have a function from the natural numbers to all integers, then clearly I have some kind of, like I can't really reverse it because there's no mapping from all the integers, all natural numbers. Unless they both are like the same infinity, but that's a whole other topic. But I don't think they do. Right, I could be wrong though. The other source of asymmetry is that functions are allowed to map many elements of the domain set into one element of the codomain. True? Right, yeah, that's true actually. So, take take the square function, right? Square 2 squared and negative 2 squared are both 4, right? So like how are you going to reverse that? You can't really. You've lost information. You've seen this, the polymorphic unit function that does just that. The collapsing can only become compounded by composition. A composition of 2 collapsing functions is even more collapsing than the individual functions. Mathematicians have a name for non-collapsing functions, injective or one-to-one. Of course, there are some functions that are neither embedding nor collapsing, those are bijections. And they are truly symmetric because they are invertible. In the category of sets, an isomorphism is the same as a projection. Yeah. So I mean, I kind of already knew this. Show that the terminal object is a unique object. Isomorphism. What is a product of 2 objects in a poset? Hint, use the universal construction. What's a poset again? In a partially ordered set. What is a product of 2 objects in a poset? So it's not just the same thing? What's bibliography mentioned? So that's what he watched, right? When writing this chapter, it's kind of whack. It was cool, you know. And then we have algebraic data types. Let's read on, because this is very closely related, and kind of like puts like some concreteness to all this. But here's a video. I don't know why my YouTube is doing that. Right. Okay. No, do not. Don't do that. Why is it a file? Okay, I don't know why I tried to cache the link. Oh, like this is actual, yeah. This is actual like watch page. It tried to. I don't know why it tried to, but okay. Because like, it's not a file, dude. There's a sequel. The AXB versus BXA example of unique up to unique isomorphism.
Those weren't exactly unique in the category, but they were certainly unique up to unique isomorphism. And this is also going to be true here. Now you can already probably guess, maybe, perhaps, possibly, that this Cartesian product has this property, but it's not the only way you could get something having this property. Here's a really stupid other way you could get something with a universal property.
Yeah.
B cross A. B cross A is so not very different from A cross B that we probably don't even think about it ever. But it's actually different because look, it's pairs BA. So now we've got the first element being in B and the second element being in A. And strictly speaking, this is in fact a different set from that set. But of course, this is also a product of A and B. And so we don't want to say that products are unique. However, there is an isomorphism between these two sets, obviously switching the 2 components over. And it's not just any old isomorphism. It's a completely canonical isomorphism that couldn't be, it's basically content-free. It's just saying, well, it's not saying anything, really. And so that kind of is telling us that we've got uniqueness up to unique isomorphism. And next time what we'll do is...
That says we have uniqueness up to unique isomorphism. Okay, so what that means is that A cross B is unique, with the exception of the unique isomorphism. And when you say unique up to isomorphism, it's saying that there may be multiple isomorphisms, I'm guessing? Right? That's my guess then. So let me just verify this. Is it working now? Okay. I just finished reading another chapter or another section from Category Theory for Programming. Am I understanding right that unique up to unique isomorphism means that a product type, well, yeah, for a product type means that for a product means that that product is unique with the exception of its single isomorphism, e.g. A cross B is unique with the exception of B cross A, and therefore that unique up to isomorphism would mean that there are multiple isomorphisms. So I've been thinking, bruh. Clo's been acting up lately. I don't really know why. Had a major outage earlier today. Supposedly it's fine. Sorry, no, that was a few days ago. Supposedly it's fine now, but yeah, it says degraded performance. Yeah. Okay. Unfortunate. Not quite. The unique isomorphism isn't about AXP versus BXA. It's about comparing two different candidate objects that both satisfy the universal property of being products of A and B. Unique up to isomorphism. If P1 and P2 both satisfy the product's universal property, then P1 roughly equals P2, because some isomorphism exists between them. For unique isomorphism, not only doesn't isomorphism exist, but it's exactly one that commutes with the projection maps. It's a comparison map between two candidates. Right?
You'll see exactly what that means, because you do have to be a little bit careful about exactly what it means. Products and co-products. These
I like this teacher, or lecturer, or whatever. Klein bottle? What? Monads. Wait, what the? 17 years ago? Nah, what? 2008, bro. I was 2 years old when this video came out. That's crazy. I'm guessing it's 2 teachers? Yeah. Man. I don't know what made him come back to write just about ends, but that's crazy. What is Klein bottle, dude? Monads. String diagrams.
Today we're going to talk about products and co-products. These are another kind of universal property which pop up all over the place. They're a little bit more complicated than what we've seen before, which is terminal and initial objects, but actually secretly later on we'll find out that all universal properties are really just initial objects somewhere. But anyway, let's ignore that for now. Products are a way of encapsulating products. Well, anyway, here's a formalism which shows how products in various different places, such as products of sets, products of categories, products of groups, products of topological spaces, are all really part of the same story. So let's just go ahead and define products in a category. A product, given, so you take a pair of objects, given objects A and B in a category, a product of them, I suppose. Product here's the object that's going to be the product, but it's not just any old object. It's got to come equipped with some structure that tells us it's a product. And what is that structure? Well, it's a pair of maps which we consider to be projection maps, one going to A and one going to B. Now, of course, it's not just any old diagram like
Projection map. Why is it a projection map? Doesn't that imply a loss of information or dimension? Yeah, okay. Does it have to be a projection map? Or like, can it be a projection map?
it's got to have a universal property. So what's the universal property here? It's a universal property saying, given any other diagram, so you take this diagram which has this kind of upside down V shape, and you say, given any other diagram with an upside down V shape like that, so it's got to have a pair of maps like this, say with an F and a G, like that, there exists a unique factorization. Unique factorization H. Now what does it mean to be a factorization? It means there's a morphism from here to here that makes the whole diagram commute. So this side, this triangle over here has to commute, and this diagram, this triangle over here has to commute. Now you'll notice that it's a bit like the definition of a terminal or an initial object, in that we said something, with those ones we had to say there exists a unique morphism somewhere, and you'll see that whenever we have a universal property, it basically comes out as saying that there's a unique morphism somewhere making something commute. And that's what it is here. So now you have to read this as a dynamic definition, because what I've written on the board doesn't actually make any sense at the moment. But
Why should you say upside down V, by the way? Because that V doesn't look upside down to me.
it's sort of, so it's given by a diagram like this, such that for all diagrams like this, there exists a unique factorization like that. So that's how you sort of dynamically read.
Ah, okay. That's weird. Hold on. So let me pull up the products category theory page again. Okay, whoops. Right. So what she's written is that for if there exists a product with morphism, if there exists a product, if there exists two morphisms from a product that go from the product to its first and a product to its second, right, so x1, x2, then for all other cases, now for all instances of where there is also a y to that and a y to that, then there exists a unique morphism from y to the product. What is y though? For every object y and every pair of morphisms, there exists a unique morphism. Yeah, I mean that's what she said basically, right? So like that is the definition. Does object y have to be of category C? Did I mention that? No. Whether a product exists may depend on C or on x and x2. If it does exist, it is unique up to canonical isomorphism because of the universal property. So one may speak of the product. This is the following meaning: if x prime is another product, there exists a unique isomorphism. Projection morphism. Sui. I mean, I guess I understand it. So if this is like if this is int, for some reason, I mean int. Let's say that this is like a string, okay, and then here we have an int bool. If there exists an int bool where I can go int and then bool, if my string can also map to int and bool, then I can have a morphism to int bool. Yeah, I guess that makes it kind of obvious. I just don't see like where's the actual like constructor happening, because like I'm trying to see it now from like a literal programming perspective, where I take two arguments and use those to form a product type. But I'm not seeing that right now. And like this is first, this is second. So that's for like destructuring. How do I construct? Like this looks like construction, but it's not. Not really. Because I would expect construction to be two different elements. So I'm a bit confused by that. And then there's Coproducts. It's kind of the opposite way. So you got this now. But okay.
This diagram A cross B here, and object.
I think I'm picking up what she's putting down. But I'm like, yeah. Let's read on here. Simple algebraic data types. Apparently pitta is a Greek thing. I did not know that. We've seen two basic ways of combining types, using a product and a coproduct. It turns out that a lot of data structures in everyday programming can be built using just these two mechanisms. This fact has important practical consequences. Many properties of data structures are composable. So I said a lot of data structures. Which ones can't be represented as products and coproducts? For instance, if you know how to compare values of basic types for equality, and you know how to generalize these comparisons to product and coproduct types, you can automate the derivation of equality operators for composite types. Yeah, in Haskell, if you can automatically derive equality, comparison, conversion to and from, string, and more for a larger subset of composite types. Let's have a closer look at product and some types of AP in programming. So the canonical implementation of product of two types in a programming language is a pair. Of two types, yeah. In Haskell, a pair is a primitive type constructor. In C++, it's a relatively complex template defined in the standard library. Okay, pairs are not strictly commutative. A pair int bool cannot be substituted for a pair bool int, even though they carry the same information. Why? They are, however, commutative or commutative up to isomorphism. The isomorphism being given by the swap function, which is its own inverse. Yep. Is there a word for functions like their own inverse? Are all functions not their own inverse? What? Sorry, are all inverse functions not also their own inverse? Nah, what? No, never mind. I mean, like, yeah, like the inverse of the inverse is the regular function. That's not what it's saying. It's saying that the regular function is also the inverse. The other interesting thing with programming types than just having like a pair, you know, is that you want to have names, right? Like, it isn't just an int and a bool. Like, it's a named int and a bool. Typically, like, if I have a what's like an actual example here, bro? If I have a user, if I have a user ID now, if I have a user, if I have an account login struct, right, or product type or record, whatever, right, and I have two fields, which are email and password, which technically is just string, right, but the way I represent it is that it's specifically an email string and a password string, so it's not just anything. But I guess that can be like, yes, like, it's weird, like the name kind of becomes part of the type. But then there's also a morphism from just like normal string to a email string. Maybe there isn't, you know? It's interesting. Does that mean that, like, do you even need variable names if you just have types? Probably, yeah. I think people have experimented with the idea of like wrapping all values in their own unique types, and it's fine. Like, it works, but you have to define like a bunch of conversions for everything, and that's just a pain. You can think of two pairs as simply using a different format for storing the same data. Big endian versus little endian. But most people don't even know what that is, but okay. Yeah, I mean, yeah, order doesn't really matter. You can combine an arbitrary number of types. Well, then again, is a list a product? And can products be ordered? You can combine an arbitrary number of types into a product by nesting pairs inside pairs. But there's an easier way. Nested pairs are equivalent to tuples. What? Yeah, what? Okay, I mean, a pair is a tuple. It's a consequence of the fact that different ways of nesting pairs are isomorphic. If you want to combine three types in a product, A, B, and C in this order, there are two ways. These types are different. You can't pass one to a function that expects the other, but their elements are in one-to-one correspondence. There's a function that maps one to another. Okay, and this function is invertible. So it's an isomorphism. These are just different ways of repackaging the same data. You can interpret the creation of a product type as a binary operation on types. From our perspective, the above isomorphism, the associativity law, except that in the monod case, the two ways of composing products were equal, whereas here they are only equal up to isomorphism. If you can live with isomorphisms and don't insist on strict equality, we can go even further and show that the unit type is the unit of the product the same way 1 is the unit of multiplication. Oh. Oh. Okay. Hold on. Why? Indeed, the pairing of a value of some type A with a unit doesn't add any information. The type A unit is isomorphic to A. Why? How about A void? Just saying. Okay, I see. So A and unit is just A. But A or void is just A. Because A or unit is legit, but A or void, you can't assign to void, so then it's just A. But for A and unit, like, I guess you just pass unit. Like, it's still there. It's just kind of dead, you know? I guess void, same case for void. These observations can be formalized by saying that set is a monodal category. It's a category that's also a monoid, in the sense that you can multiply objects. So in this case, Cartesian product. I'll talk more about monodal categories and the full definition in the future. Again, there's a more general way of defining product types in Haskell, especially as we'll see soon, when they are combined with some types. It uses name constructors with multiple arguments. A pair of, okay. I'm sorry, I feel like we skipped over this. I didn't fully catch the reasoning here. Why is units not adding information theory? Like, is is it just considered not useful information? Okay, I see. So what's this, by the way? Product types. 6.1. Product types. I don't know why I say that then. Okay. One could consider the unit type. Yeah, the singleton type. The singleton category. Unit. To be the what's it called? Is the unit to be the unit of a product monoid, since adding since A and unit isn't adding any additional useful information. We could merely, yeah. Likewise, I believe this is why void is the unit, is a unit of a coproduct monoid, since A or unit is providing a useful distinction, whereas A or void is not, since void is practically inaccessible. As the book mentions earlier, this is another reason why a coproduct is often called a sum, since products are akin to multiplication to the multiplication monoid with a unit of 1, while coproducts are akin to the addition monoid with a unit of 0. Perhaps. Arthur Morgan. What? Sexter Morgan. Here data pair A and B is named type by as A, B. Okay. The first line is a type declaration. Type constructors. Since the namespaces for type and data constructors are separate Haskell. If you squint hard enough, you may even view the built-in pair type as a variation on this kind of declaration, where the name pair is replaced with the binary operator comma. In fact, you can use comma just like any other name constructor and create pairs using prefix notation. What? That's cool. That's what I want for my language, low-key. That's really cool, actually, yeah. Similarly, you can use that to create triples and so on. Wow. Okay, makes sense. Wait a minute. Okay, I tried. Oh my god. Okay, what are these random ass examples each time? Can I print? So I assume I can do, first of all, plus 5 and 3, right? But if I do 5, 3, and 8, it does not work. Can I do plus plus? Okay, I see how this could go wrong. Okay, let's try times. Never mind. Let's do comma. 5, 3, and 8. Can I print a thingy? A sum type? No. Okay. Whatever, dude. Which is just a product of string and bool. But it's given its own name and constructor. Yeah. Okay. Give names to components. A product type is with name fields called a record. Yeah. So like the reason I skimmed through that is because I already know this. Let's have a look at a simple example. We want to describe chemical elements by combining two strings, name and symbol. This code is error prone, how to read and maintain, what you need to define a record. Yeah, okay. The functions access these fields. For instance, atomic number E retrieves the atomic number E filled from E. Yeah. The only thing is that they're globally scoped. With record syntax for element, our functions such as symbol becomes more readable. We could even use the Haskell trick of turning the function is prefix of into an infix operator by surrounding it with back quotes and make it read almost like a sentence. Yeah. Sum types. Just as a product in the category of sets gives rise to product types, the coproduct gives rise to sum types. How long is this chapter, by the way? Not long at all. The canonical implementation of a sum type in Haskell is either A, B, left, okay. And like pairs, either are commutative up to isomorphism and can be nested. So it can be nested and the nesting order is irrelevant up to isomorphism. So we can, for instance, define a sum equivalent of a triple. Yeah. And so on. It turns out that set is also a symmetric monoidal category with respect to coproducts. The role of the binding operation is played by the distort sum, and the role of the unit element is played by the initial object. In terms of types, we have either, and void as 0. So either A or void is isomorphic to A. That's because there's no way to construct a right version of this type. Yeah. So symbolically, A plus 0 equals A. Some types are pretty common in Haskell, but their C++ equivalents, unions, or variants are much less common. There are several reasons for that. Yeah, it's ergonomic as hell. First of all, the simplest sum types are just enumerations, and I implement using enum and C++. The equivalent of the Haskell sum type is C++ this, right? Like, oh my god, it looks so cool. Yeah, bool is printed bool in C++. Simple sum types that encode the presence or absence of a value are variously implemented in C++ using special tricks and impossible values like empty strings, negative numbers, null pointers, etc. This kind of optionality if liblet is expressed in Haskell using the maybe type. I mean, null pointer is a particular trick. Well, no, yeah, null pointer is a trick. Because like it's changing the meaning of 0, right? The maybe type is a sum of two types. You can see this is if you separate the two constructors into individual types. The first one looks like this. It's an enumeration which, with one value equal nothing. Yeah, equivalent to the unit type. Yeah. Nothing is just nothing. It is actually interesting. Why doesn't Haskell maybe use unit for maybe? Like, will that low-key make sense? Out of curiosity, why doesn't Haskell, and indeed other languages, just use unit for their maybe/optional or option types, rather than a special other singleton type like nothing or none? Good instinct. Maybe A is basically either this or A. is a tagged singleton. But you can't use bare singleton directly because maybe A is a sum type, not just a product. You need two things. What? A tag, yeah. Oh yeah, they need a name, don't they? Is that true even? If you try to use this alone as an empty signal, you're able to distinguish maybe A from plain that. It's true. Yeah, the tag. I'm still trying to think what the best way to do tagging is for some types. And it's weird that product types don't need tagging, but some types do, you know? Like, I wonder what the theory would be behind that. So I like kind of like represent to show that. Probably because with product types, there's just one morphism, right? Like one it's really obvious from the context which one you mean. Whereas with some types, because there are multiple morphisms to one type, you need to specify which one you mean in that context. I said that so badly, but I think the idea is there. So if I define, so like products don't need it, but for some types it's basically specifying an overload, right? Like it's almost like having different constructors with explicit names, because each constructor takes the same arguments. Now that isn't true, but they can take the same arguments, but not necessarily, right? Like if I had a sum type which was literally just like an int or a string, like if I pass an int, it's pretty obvious I mean the integer, right? So yeah, actually that's interesting. I guess you only need to really tag them if there is some ambiguity in the overload. So I wonder how that could go. This is some types. This is 3, right? Don't know why I deleted everything there. That was not. Sorry. Just thinking. No. Yeah. Just thinking. It doesn't really. You only really need tags on some types. For ambiguous cases caused by identical constructors. Very similar to how you would want a differently named constructor for a product type. No, similarly how a product type with two constructors that take the exact, two constructors of the exact same signature would also need to be to have some kind of tagged distinction. That is to say, there's no need to tag something like int or string, because it is obvious what you want, because it's obvious which fields is being targeted based on the type of the input being passed. Because like it's just weird to me how, yeah, it's like seems to be only be a thing for some types, like sum type SUM. More complex sum types are often affected in C++ using pointers. A pointer can either be null or point to a value of a specific type. For instance, a Haskellist type, which can be defined as recursive, in C++ uses the null pointer trick to implement the empty list. Yeah, so it does. Notice how the two, it's actually very interesting how we think about it this way, isn't it? like in Haskell, it's either, it's either nil or that. Whereas here, I mean, okay, to be fair, it's still like conceptually the same thing. Notice how the two Haskell constructors nil and cons are translated into a validity list. Okay. Haskell data structures are immutable, yeah. So an object that's just energy will never return to nothing. Similarly, an empty list will forever be empty, and a list of 3 elements will always have the same 3 elements. It's this immutability that makes construction reversible. Given an object, you can always disassemble it down to parts that were used in construction. This deconstruction, there's the word, is done with pattern matching, and it reuses constructors as patterns. Wait, what? But C++... hold on. You can deconstruct... No, but like... You can destructure types in C++ 2, so I don't really understand that. What, like, immutability? Like, what? The first part of the definition of maybe tail uses the nil constructor as a pattern, and returns nothing. The second part uses the cons constructor as pattern. It replaces the first constructor argument with a wildcard. Because we're even more elaborate, some types are implemented in C++ using polymorphic class hierarchies. A family of classes with a common ancestor may be understood as one variant type, in which the vtable serves as a hidden tag. What in Haskell would be done by pattern matching on the constructor and calling specialized code in C++ is accomplished by test patching a call to a virtual function based on the vtable pointer. Yeah, you can kind of get like ad hoc. Is ad hoc the word? But like poor man's pattern matching through overloading, and that's literally what the variant or the visitor pattern is. And like it works to an extent, but we do want to have pattern matching in C++, and it will come eventually. You will rarely see union used as a sum type in C++ because of severe limitations of what can go into a union. You can't even put a string into it because it has a copy constructor. Okay, I didn't know that. Copy constructors restricted it. Algebraic types. Taken separately, product and sum types can be used to define a variety of useful data structures. But the real strength comes from combining the two. Once again, we're invoking the power of composition. Let's summarize what we've discovered so far. We've seen 2 commutative monodal structures underlying the type system, sometimes void and unit type unit. We like to think of them as analogous to addition and multiplication. In this analogy, void would correspond to 0 and units to 1. Let's see how far we can stretch this analogy. For instance, does multiplication by 0 give 0? In other words, is a product type with one component being void isomorphic to void? Yes, because then you can't construct it. That's crazy. For example, is it possible to create a pair of, say, int and void? To create a pair, you need 2 values. Although you can easily come up with an integer, there is no value of type void. Therefore, for any type A, the type A void is uninhabited, has no values, and is therefore come to void. That's crazy. Yeah, cool. Hold on. The idea that a product type represents multiplication, or like is analogous to multiplication, with unit being the neutral / unit value, objective value. I want to use precise language here. Neutral element. Even extends to how multiplication by 0 is 0 and it results in 0. If I have a product type containing void, then it becomes impossible. Yeah, such as int void. It becomes impossible. It becomes impossible to fully construct an instance of that type, and thus the entire type is effectively void. Partial construction is an interesting idea. I just don't really know how that would work. Yeah, it wouldn't, like, it'd have to be like maybe void, you know, for that to kind of make sense. Distributive property. Does it also hold for products in some types? It does. Up to most as usual. The left hand side corresponds to the type. A or A and B or C equals A or A and B or B or A and C. True? True. That's cool again. Furthermore, A times B plus C equals A times B plus A times C is analogous to how the type A and B or C is equivalent to A and B or A and C. Bro, I want to get back. I want to watch this again. Continue. Yeah, cool function actually. This isn't built in, right? The case of statement is used for pattern matching. Okay. The E in case E of will be equal to left high. It will match the pattern left y, substituting high for some y. I'm not going to prove that these functions are the inverses of each other, but if you think about it, they must be. Mathematicians have a name for two such intertwined monoids. It's called a semi-ring. What the hell? It's not a full ring because you can't define subtraction of types. That's why a semi-ring is sometimes called a rig, which is a pun on ring without an n, negative. Dude. Murder whoever made that convention. We're barring that so we can get a lot of mileage from translating statements about, say, natural numbers, which from a rig to statements about types. Here's a translation table with some entries of interest. So void unit, A plus B is this, A times B is this, 2 equals plus 1, bool equals true or false, 1 plus A, nothing, interesting how like this very much correlates to size, right? The size of the type. So this gives this is labeled as a semi-ring, so called because a ring would also define, as a full ring would include subtraction, whereas this does not. For some unknown reason, someone thought it would be a good idea to also label this as a rig, a pun on ring without the n for negative. I mean, look, it's cool, okay? It's cool. It's just a bit ridiculous. The list type is quite interesting because it's defined as a solution to an equation. The type we are defining appears on both sides of the equation. If we do our usual substitutions, and also replace list a with x, we get the equation x equals 1 plus a times x. We can't solve it using traditional algebraic methods because we can't subtract or divide types. We can try a series of substitutions where we keep on replacing x on the right hand side with 1 plus a times x. So it will be 1 plus cons a to list of a. So let's say I have one element such that a is it's an infinite sum, right? Like, I can't say that a is 1. Wait, yeah, x can x be, no, x can't be 1 either. We can't solve it using traditional algebraic. Yeah, no, because like it's not concrete. But we can substitute. So x equals 1 plus a times x. We end up with an infinite sum of products, which can be interpreted as a list is either empty, 1, or a singleton. Sure, dude. Oh, I see. So it can be empty, it can be this, it can be this and this, it can be this and this and this, it can be this and this and this and this. So a list is a product type, pretty much, right? A string of A's. That's actually a really cool proof. There's this really cool way to show what a list truly is. Well, to show what a list truly is. Actually, let me write it out. Firstly, we have the definition for a list written with natural numbers, or represented. So the code would be a list a equals nil, or cons. Can I do this instead? I don't know if that's valid, but I'll do it for now because that's just easier to read for me. Okay, so this would be x equals 1 plus a times x. If we keep substituting for x, we start to notice an interesting if we start substituting for x, we begin to note, although it is infinite, although it does go, although we would end up going on for infinity, an interesting pattern does emerge. So if x equals 1 plus a times 1 plus a times x, right? Which equals what's the way to use? Just equals, yeah. which equals 1 plus a plus a times a plus a times x, or a squared. But we'll do it times a. I'll start using the actual symbols here. There's asterisk with backslash times. And I'll try to use parentheses here to be a bit more readable. Equals a plus a times a. Yeah, if we do x equals 1 plus a plus a times a plus a times a times a plus a times a times a times a plus ellipsis. Use C dots here. Yeah. This literally reads as a list X. Okay, no, a list is either a unit, so empty, a single element, two elements of the same type, three elements of the same type, four elements of the same type, and so on. Hold on. Would we say either for two things, right? Is a unit and a type, or a single type, or two elements of the same type, or three elements of the same type, or type, and so on. Yeah, very cool, very cool. That's pretty much that's much more to listen than that, and we'll come back to them as other recursive data structures up to a number of functors and fixed points. Solving equations with symbolic variables, that's algebra. So it gives these types their name. Algebraic data types. What? Seriously? It is this kind of algebraic solving that lends name to this concept in programming, algebraic data types. The more you know. So this is a different section, 6.4, algebraic data types. Now, algebra of types is called. Cool. Finally, I should mention one very important interpretation of the algebra of types. Notice that a product of two types A and B must contain with a value of type A and a value of type B, which means both types must be inhabited. A sum of two types, on the other hand, contains either a value of type A or type B. So it's enough if one of them is inhabited. Logical and an OR also form a semi-ring, and it too can be mapped into type theory. Holy moly, are you serious? False is void, true is unit. Oh my god. A or B? Yeah. Unit or unit is unit. What? Unit or unit is unit. Void unit is void. Sorry. I mean and, sorry. Void and void is void. Unit and void is void. But only unit and unit is unit. That's crazy. But then, for OR, void or unit is unit. Unit or unit is also just units. Void or void is not representable. That's crazy. What? Boolean algebra also forms a semi-ring where false is where false is 0 and true is 1. Not really though. Where false is void and true. Actually, let me use these names instead. False is void and true is this. That's crazy. Challenges. Should I orphimism machine maybe A and either this A? Okay, cool. That was actually a question I had. Here's a sum type defined in Haskell. We want to define a function like area that acts on a shape. We do it by pattern matching on the two constructors. C++, hell no. Continuing with the current SW example, we can easily add a new function circ. Okay. So that A plus A equals 2 times A holds for types up to isomorphism. Remember that 2 corresponds to bool, according to our translation table. Does it? 2 is bool? Okay. Why? Yeah, I'll tell you why. True or false? I guess it's binary, right? So yeah, it would be true or false. So A plus A would be A plus A would be an A and an A, right? 2 times A would be a boolean of A. Or no, sorry, it's A or A, isn't it? Jesus Christ. Yeah, sorry, it's A or A. So int or int. 5 or 5. For 2 cross A, it'd be a boolean and int. But they're tagged, right? Yeah, so it's just like one could be like the first state, one's the second state. So like it's not necessarily bool as much as it is just like some binary data, some binary value. But yeah, okay. Cool. Functors is next. Okay, cool. So we're going to reserve functors for the next reading, but we get functors in programming, functors as containers, composition, and challenges, of course. Then we get functoriality. Don't know what that is. Heard about a functor. Oh my, there's a lot. Oh my days. Okay, have a look at that. Function types, whatever that is. Okay, so I guess universal construction explains in more depth. That's good, because I didn't really understand that. We get currying. Cool. I definitely want to see currying from a category theory perspective. I feel like it's quite simple. Probably very similar to the Haskell idea. Don't know what exponentials are meant to be. Like in category theory. I guess it's just like a way to represent a repetition of a product type. But I don't know. don't know what that is. Exponential algebraic data, don't know what that is. Curry-Hart isomorphism, you've heard of it. And then there's natural transformations. I've heard of natural transformations, but I didn't really understand them when I first learned about them as well. So yeah, this would be very interesting. But cool, we're now up to chapter 7. So, quick little recap here of what we covered today. For every C, there exists the opposite category, C opposite, right? For product types, you can consider, well, you have a semi-group, right? So you can consider for products and co-products a unit type. Sorry, the unit element or object or whatever is analogous to 1 in multiplication, because if you multiply by 1, or if you cross with the unit type, then you get the same thing. And if you add it, then it counts, but not if you multiply it. And void is 0. Okay, so that whole thing just explained really confusingly, to be honest, but in my own, I mean, not really, but like it's just kind of hard to summarize because it's quite particular. For some types, I was thinking that you only really need to tag some types that cannot be easily distinguished in the same way that you would have to distinguish different constructors for product types. So that, because like it's just a question of, do you have conflicting morphisms? Like if there are multiple morphisms from A to B, then it means that you need to have some kind of distinction, right? So it's also much that some types need to be tagged. It's more so that conflicting morphisms need to be tagged, and it just so happens that the place that is most likely to occur is in some types. So I'll definitely check that out and see what I can do about that to make it feel natural, to make it feel like intuitive and natural and like global, as opposed to like just like a sometimes thing. Because then other features and areas of the language will also benefit from that. Same thing as I said before, with the product type being 0 and whatnot, but also how you have this thing, right? So A times B plus C is literally analogous. The fact that A times B plus C equals A times B plus A times C is analogous to how the product type of A and B or C is, conceptually equivalent to A and B or B and C. A and B or A and C. And that's called a semi-ring. And then a ring is called semi-ring because it doesn't have subtraction. A ring would have subtraction. A rig is a pun where n is negative or negation, and that's why. But that's a rig is just a semi-ring. But I believe they are called semi-ring, where in Haskell, so that's good at least. Then there's algebra of types, so the fact that you can like represent these things as numbers and stuff is pretty cool. And yeah, that list, the whole list thing, right? Where like a list recursively expands to 1 plus A and A plus A times A times A plus A times A times A times A, and so on and so forth. And that corresponds to saying it's either the unit type, which we interpret as nothing in this case, or it's one element, or it's 2 elements of the same type, or it's 3 elements, or it's 4 elements, or it's 5 elements, and so on and so forth, to infinity. Maybe there's a limit there somewhere, but I don't know how you would even do that. Well, I mean, if there's a limit, then it's just not recursive, is it? So yeah, it would just be really a long definition. Boolean algebra also forms a semi-ring where false is void and true is that, which is pretty cool. And they're called algebraic data types because of the whole algebra thing. So there you go. Not like crazy mind-blowing stuff, but obviously some very interesting things. The next chapter, functors, will be the true, where things get real, because functors are morphisms between categories, to my understanding, and that is where things get freaky. So yeah, good. 2 chapters today, tomorrow, at least 1 more. Functors isn't that big of a one, The one after it with functional reality, that one will be longer. So I'll see how far I get, but I am determined to get through like most of this book, if not finish it by the time I start uni, or move into my into my accommodation, which would be in roughly 2 weeks. So, like, surely I can finish a book in 2 weeks. Come on. Even if it is category theory, whatever. So subscribe for more category theory reading. I guess most of my videos will probably be focused on category theory for like the next few days or whatever, because there is not really anything else I'm doing right now. Like I'm not working on my game at the moment. I guess I might come back and work on my game at some point in C++, but when I do that, it would be specifically to implement concurrency and kind of change my game like engine to use concurrent signaling or whatever, like event handling, kind of like Scratch style, not really, but like that kind of like drastically different approach to mapping out a game. That's what I want to do with my game engine. So that would be quite drastic and definitely not easy. And I kind of want to, like, I don't want to delay it necessarily, but while I'm focusing on this really hard topic, which is category theory, I don't want to also be focusing on this really hard topic, which is making a game engine with concurrent programming in C++. So, like, if I delay that, it's just because I'm, I want to like focus on one thing. Like, cause like usually I do have lots of different projects going on, but it's different when I can like kind of divide my attention. Like for these two things though, like they are both so equally. I mean not equally, but like they're both really high, like focus level and like difficulty, and like I'm learning a lot as I go through them. That switching between them isn't as efficient. So what I'm saying is I'll probably hyper focus on this before I go on to hyper focus on the other thing. Otherwise, there's some other things I'm doing, like with like the JPI launcher GUI. That's fairly straightforward. I mean, not really, but the bigger issues I can't just due to my limited resources on my computer, I can't really record my progress on that, because I can't have Steam open testing launching this GUI launcher for the game while also recording on Obsidian on a ThinkPad with an integrated graphics card and 16 gigabytes of RAM. So it's just not gonna really work out that way, unfortunately. And there's nothing else I'm really doing right now. Yeah, like in terms of projects, like there's some things I want to, like maybe I'll take a day or something, or like a day or two to fix my art setup with my workspace switching, as I kind of mentioned towards the beginning of this video, just to get that sorted, because that's kind of annoying. But yeah, I don't even know why I'm giving out such a plan, but like just to say this is what my plan is for the next few days, because I want to commit. And I'll keep watching The Mentalist, because that show's awesome. Okay.